Amy and Ben are playing a game. They both alternate playing pieces on any empty square in a 20 by 20 grid. Amy plays red and Ben blue. However, Amy has the added condition that she can't play on any squares that are a root 5 unit distance away from any of her current red pieces. Ben, though, can play on any empty square. These two will continue placing pieces one by one until there are no more squares left on the board, or until Amy is unable to play any more of her pieces, with the aim being for Ben to try and deny as many squares as possible for Amy, while Amy tries to maximize the number of squares that she has her own pieces on. Given Amy's restriction, an interesting question is raised. What is the maximum number of pieces that Amy can guarantee that she can place, no matter what Ben does? This question, in some alternate wording, was asked in the International Mathematics Olympiad, or IMO, in 2018, which is arguably the hardest high school math competition on the planet. The way the question is put there, though, is kind of intimidating. It's quite long, it's 142 words, there's a square root thrown in there, and there's a bunch of random looking variables, and so at first glance, this might look like kind of a pain to deal with. And it is, but there actually is a really elegant way of looking at this question. This more elegant way arises if we take a close look at the range of Amy's stone. You might have noticed from the intro that Amy's stone's range is very similar to another piece from an ancient board game, chess. In fact, its range seems to be exactly the same as the knight. It may be slightly unclear as to why this is the case, so let's take a look at that distance of root 5 units again. Whenever there's distance and square roots involved, it's usually a good idea to look for a connection to the Pythagorean theorem. A squared plus b squared equals c squared. Here, it's quite simple to find the connection. The distances between any two squares on the grid can be modeled with a right triangle, and that cannot be root 5 units thing means that the hypotenuse of this triangle, the actual distance between the two squares, cannot be root 5 before Amy plays there. So what you have to check is what integer values for the base and the height of this triangle create a square root of 5 distance. Well, we can just brute force all the possible integers here. It's really not that many. And as you can see, the sides of the triangle can't be 2 and 1, no matter the direction. If you want to, you can quickly verify this by plugging it into the equation, and indeed 2 squared plus 1 squared does equal square root of 5 squared, no matter if one of them is negative or if you switch around the positions of the 2 and the 1. And if you look at all of these arrows, it is identical to the way the knight moves in chess, characterized by this famous L shape over here. So now that we know that Amy's stone moves like a knight, let's look at how a knight moves. There's something a bit cool about the squares that are a knight's move away from each other. Feel free to pause and try and figure out what exactly we're talking about here. Well, hopefully you found it. And it's that every single square that is a knight's jump away is of the opposite color from the original square. If the knight started out on a black square, every single square it can move to is a white square and vice versa. To verify this, you can see that moving 2 squares in any direction doesn't actually change the color. It's when a knight actually moves the 1 in that perpendicular direction, which results in the color switch. So, using this color idea, can we come up with a plan for Amy? Because of this new color fact we found, what if Amy just kept her pieces on one color? Let's say she chooses black. That way, since her pieces on black squares only restrict her from playing on white squares, she can keep playing on black squares as much as she wants without being restricted. Well, Ben, sensing Amy's strategy, would keep his own pieces only on black as well. Therefore, Amy only gets half of all black squares, or 1/4 of the entire board. Thus, the minimum number of pieces Amy can place on the board is 1/4 of the total number of squares, or 120 by 20 board. But Amy, in these scenarios, usually gets more than 1/4, given the fact that there are some white squares that are not a knight jump away from any of her current pieces. So the question is, can Ben systematically prevent Amy from getting more than 100? Or maybe she's destined to get more, maybe 101 or 102. And if so, what is the maximum that she is guaranteed to get? To find out, let's switch back to how a knight moves. Out of the 8 arrows, 2 are always quite close to each other. And if you look a little hard, both are in fact a knight move away from a different shared square themselves. This creates what I'll call a 4 cycle, which are basically 4 squares that form kind of a cycle of knight moves. If you zoom in on a single 4 cycle in a 4x4 grid, you can see that Amy wants to play on the opposite side of this cycle, denoted with a blue X. She wants to do this because, in doing so, there are no extra black squares she is restricted from. The black squares she can no longer play in kind of overlap with each other if she were able to play in both of these white squares, therefore maximizing the number of squares she can play on in the future. Therefore, Ben has to stop Amy from playing there, so he plays there instead. So Amy is restricted to getting only 1/4 of every single 4 cycle, as she cannot play in any of these black squares either. If you were to take this a step further, you could see that this 4x4 grid can be split into 4 different 4 cycles. I'll mark them all with different colors here. And the plan for Ben is just to block Amy from playing on the spot of the 4 cycle that she wants to. Simple as that. And so no matter where Amy plays, she always ends up with the same result. For example, if Amy plays here, Ben plays here. If Amy chooses instead to play here, Ben will instead play here. I'll play an example of this to help show it in action. Amy, therefore, always gets only 1/4 of every 4x4 grid. Now, if we go back to our original 20x20 board, we realize that this board can actually get evenly split up into 25 different 4x4 grids. And if Amy can get a maximum of only 1/4 of each of these 4x4 grids, that means Amy can only get 1/4 of the entire 20x20 grid, which means Amy can only get 100 squares if Ben is smart. But that isn't the end of it. One of the facets of these kinds of IMO problems is not just the intuition or the idea, although of course those are incredibly important, but also the formalization and how you would actually write the answer itself, which is not immediately clear, especially in mathematical terms. So let's start instead by writing what we have right now without worrying about changing all of the terms or writing any of the mathy stuff. So to sum up what we figured out so far, the answer K is 100 because Amy can keep her pieces on only black squares, because no black squares are an L shape away from each other, and Ben can prevent Amy from getting more than 100 because of his nice little 4-cycle trick. So let's start by formalizing the idea of a black square. To do this, you have to notice something about the checkerboard pattern. So I'll put the 20x20 checkerboard on a grid from 1 to 20. The board obviously alternates white, black, white, black, white, black, and so on. So a black square is really just a way of saying an even-numbered square on this grid. So a black square is just a square where x plus y is an even number. So we can just replace that in our solution. The next thing to change is the notion of what an L shape is, but this is pretty easy. It's given in the question. An L shape is just a distance of root 5 units. So you can pretty easily change that. And the last thing you have to formalize and write down is this little 4-cycle notion we have going on here. So how would we put, words and numbers to it? Looking at the 4x4 grid we made with the different colored crosses, we can turn each 4-cycle into its own number. So you turn all the red crosses into 1s, all the blue crosses into 2s, and so on. So now we can just say that whenever Amy plays on a 4-cycle of a certain number, Ben plays on the opposite site in that 4-cycle of the same number. And that is our answer. Pretty cool.